This is an RNZ podcast.
Ngā mihi nui and welcome to Elemental, a podcast from RNZ celebrating 150 years of the periodic table. I'm Alison Balance.
And I'm Allan Blackman from the Auckland University of Technology. And our random walk through the chemical elements has finally brought us to the very beginning. Number 1. Hydrogen. I think we could reasonably describe this episode as hydrogen, number 1 in the universe, as it's the oldest, the lightest, and the most abundant element in said universe.
Good old hydrogen, eh? Now, relax and just sit back a bit, Alan, because I'm going to take away this next bit. Vital statistics.
Ooh.
Symbol H for hydrogen. Atomic number 1. Up there in first place in the top left corner of the periodic table. Now, you've said it's the oldest, lightest, and most abundant. Does being number 1 also make it the simplest element?
Yes, indeed it is. And normally it contains a single proton and 1 electron.
No neutron?
Well, yes. Well, there are forms of hydrogen that do contain 1 neutron. We call that deuterium, and 2 neutrons, which we call tritium, and which was discovered in 1934 by good old Ernest Rutherford.
That great Kiwi.
Oh, yes, indeed. And normal hydrogen, if we're going to be absolutely correct, the one that's only got 1 electron and 1 proton, we really should call it protium rather than hydrogen.
But we don't. We just call it hydrogen.
But we don't. You're right. We just call it hydrogen, which can be confusing to chemists. But anyway, so we'll come back to deuterium in a minute.
So when did we find out about hydrogen?
Go all the way back to 1766, and a fellow by the name of Henry Cavendish was the first person to recognise that hydrogen gas was in fact a discrete substance, and that when you burn it, you form water. And his name for it was inflammable air, which is kind of nice. That's in fact how it's got its name, because in Greek, hydrogen means water former or water creator, a quite appropriate name in this case.
Brilliant. So you've mentioned it was the oldest of the elements?
Indeed. So there were only 3 elements formed in the Big Bang. That was hydrogen, helium and lithium, the first 3 elements on the periodic table.
And the most abundant?
Yes, indeed. Hydrogen is the most abundant element in the universe. So 88% of all the atoms in the universe, and again we're talking observed atoms like we were talking with helium, are in fact hydrogen atoms. And hydrogen is the fuel of the stars, essentially, and it's the reason why stars glow, if you will, because hydrogen undergoes a process in stars called nuclear fusion. And the first step of this particular process involves hydrogen nuclei, as the name suggests, fusing together, and they form helium nuclei. And the thing with that is that when this process happens, you get truly mind-boggling amounts of energy released. So to illustrate that, if we look at our sun, for example, our sun converts about 600 million tonnes of hydrogen per second to helium.
Per second?
Per second.
Crikey.
And as good old Einstein said with E equals mc squared, the equivalence of energy and mass, about 5 million tonnes of matter are converted to energy during this particular process. And that just releases a huge amount of energy. So nuclear fusion, this occurs in the sun. It also occurs in a hydrogen bomb. And the thing is, if we could control this enormous amount of energy that we get in nuclear fusion, then we would be set for our energy problems forever, basically, because nuclear fusion is potentially a limitless and clean source of energy. And again, to just illustrate how much energy you can get out of this, you take 4 grams of hydrogen. If that undergoes nuclear fusion, that's going to release the same amount of energy as burning roughly 60 tonnes of oil. Astonishing. Absolutely mind-boggling fact, that.
You'd have to have a much smaller fuel tank in your car if you were trying to run it on hydrogen, wouldn't you? I'll just have 4 grams worth, please.
Indeed, yes, yes.
Now, you mentioned that 88% of all atoms in the universe are hydrogen atoms, so it's massively abundant in the universe. Is it really common on Earth then?
Oh yes, very much so, but not in what we call its elemental form, which is hydrogen gas, which is made up of hydrogen molecules, H2. So there's a tiny amount of H2 gas in the atmosphere, but really on Earth we don't get it in its native state at all. And it's pretty much found all of the time bonded to other atoms on the planet. And the most important compound undoubtedly of hydrogen is in fact water, H2O. And a little known fact here, if you're a chemist, you are meant to call water, in fact, oxidane, which is its real chemical name.
Oxidane? Can you please explain?
I'm not sure I can. Well, I'll give it a shot, but there's a group of people who make the laws for such things called the International Union of Pure and Applied Chemistry, and they have decreed that following molecules like CH4, which is called methane, or SiH4, which is called silane, or pH3, which is called phosphane, H2O, or OH2, if you will, should then be called oxidane. Needless to say, nobody calls it that. Everybody calls it water, but those are the rules, apparently.
Yes, I think that name will remain a slightly niche name.
Yeah, it's a pub quiz name, that one, I'd say. So hydrogen is present not only in water, but in every single organic compound on the planet. And in fact, we use hydrogen gas in industrial processes. The main source of hydrogen gas is in fact natural gas. Again, it's coming from basically dead things. And if you take natural gas, which is mostly methane, and heat it with steam at around about 1,000 degrees, you end up with hydrogen gas. And why are we interested in this? Well, if you've ever seen a hydrogen balloon explode, for example, you'll know that you get a heck of a lot of energy coming out of that. So we can take hydrogen gas, we can burn it with air, we get a significant amount of energy, and the beauty of this is that the byproduct of this combustion process is just water. So you can't get cleaner and greener than this. So obviously there's an enormous amount of energy in just combusting hydrogen gas as a source of energy for the future, clean and green.
I have to say it all sounds very circular. Water features a lot in the making of it, the breaking of it. Now, you were going to tell us more about deuterium.
Yes, indeed. So deuterium is an isotope of hydrogen. And remember, the definition of an isotope is an atom that has the same number of protons but different number of neutrons. So in 1931, a guy by the name of Harold Urey discovered deuterium, the first isotope of hydrogen. And that was such a great discovery that 3 years later he was awarded the Nobel Prize in Chemistry for this. Why is this interesting? Well, you can make water in which all of the hydrogen atoms have been replaced by deuterium atoms. And this is called heavy water. And it's used as a moderator in nuclear reactors. And if we go all the way back to World War II, when you remember there was a big sort of race for the atomic bomb, well, D2O, or deuterium oxide as it's called, could have been very, very important in the development of a German atomic bomb. There was a plant that made heavy water in Norway, and this was sabotaged by some very, very, very brave Norwegian and British folk, and that set back the possible German atomic bomb.
You mentioned balloons just before. I'm thinking hydrogen is really light and it floats, so we have tried to use it to fly, haven't we?
Oh, yes, very much so. And even all the way back to 1783, which rather amazed me. So we've known of hydrogen since 1766. So a few years after that, people realised the fact that, yes, you could use hydrogen gas to lift things because it is less dense than air. And so they used it way back then to fill balloons that could, in fact, carry people. And this went on, indeed, till the early years of the 20th century, where it was used in airships, which were absolutely massive, massive, massive things, like 200 metres long, all filled with hydrogen, unfortunately, which, as we know, burns very, very well with oxygen. And there were two airship disasters, the R101, which was a British airship, and the one that everybody knows was the Hindenburg, which was in 1937. Basically, that put a stop to airships, probably well and good, yeah.
Give me an interesting fact about hydrogen.
Okay, well, here's a couple of interesting facts. You've all heard of acids, for example, and acids are intimately associated with hydrogen. And in fact, we talk about the concentration of hydrogen ions in aqueous solutions, and we call this essentially the pH scale, or the pH scale is based upon this concentration of hydrogen ions in aqueous solutions. One of the definitions, in fact, of an acid is that an acid is a proton donor or a hydrogen ion donor. So all of acids and bases, all of that chemistry is to do with hydrogen ions. And the second important thing about hydrogen is that it can mediate a force called the hydrogen bond. And hydrogen bonds are extremely important not only in chemistry but in biology, for example, where there's a little molecule that we all have inside us called DNA, and it's double-stranded, and it can wind up and unwind, etc., etc. And those two strands are held together by hydrogen bonds. So very, very important in that respect.
So hydrogen really is number one in the universe, especially for life as we know it. This has been episode 36 of the RNZ podcast Elemental. You can find us online at rnz.co.nz/chemistry or on your favourite podcast app.
And we're back next time with indium. But until then, it's goodbye from me, Allan Blackman.
And me, Alison Balance. Mā te wā.